Good morning. Every good presentation starts with technical difficulties, so that's a good start. Quick agenda here. I guess first off, I'm Dave Brodowski, TrueTech Bridge, Robert Cavaliero with Specification Products. We're excited to present on these three deck technologies that were used to improve service life for a bridge with the Indiana DOT in Fort Wayne, Indiana. First, kind of provide a little bit of background just on the importance of construction quality on deck service life, and then we'll get into each of these technologies in more detail. So we don't talk a lot about bridge deck preservation in terms of the initial construction as much as, around here we talk about treatments available on older bridges, but, new construction has a huge impact on on long-term service life. So I highlighted two major points from the deck preservation resource guide here about the impact of construction quality, which they say is the first and most salient factor to optimizing service life for a given bridge deck design. And then the second point here, it's important to take care of the deck because it's like a roof protecting all the underlying elements. So pretty much like the previous presentation, the trickle-down effect of deterioration is a thing that we all want to prevent. So we do know bridge decks are eventually going to crack, but early age deck cracking can be a real problem since maintenance and preservation is needed too soon after construction. Jim Nelson with the Iowa DOT, he's the head of AASHTO T9. He did a webinar recently on IDOT's remediate. It was a webinar to remediate bridge deck cracking. He referenced early age deck cracking as a significant problem. So you can see this bridge here, 2019 it was constructed, within 2 years developed transverse cracking across the majority of the deck. There's a lot of reasons why early age cracking can occur, but it's something we're all trying to get a handle on because now it's a maintenance problem with treatment needed within just 2 years. And we all know even getting back to that bridge, doing maintenance of traffic is going to be a huge expense to get that work done. But decks are eventually going to crack, and as we know, the efflorescence appears, moisture starts to penetrate the deck, reinforcing starts to deteriorate, cracks start to grow, then over time, obviously rust, deck spalling, delamination start to occur. Obviously, we want to make this push out into the future as long as possible. So how do we improve bridge deck construction quality? Today we're going to focus on three aspects of construction and then new technologies for each. So the first is deck forming, then concrete curing, and then concrete maturity testing. So for example, how do deck forming systems influence performance on service life? Do contractors remove wood decking too soon? Does lumber pull moisture from the concrete during the curing process? Do corrugations of metal forms restrict concrete as it shrinks, putting stress into the deck? Temperatures, wind, humidity, travel time, pumping operations, compaction, vibration, all of these factors, how does that influence deck performance? So another thing to keep in mind is, are contractors adding too much water as they're trying to finish it? And when do we open the bridge deck to traffic? QA/QC, another important topic in our industry today. We've been doing cylinders for 100 years, but are those cylinders cured in a separate environment? Are they the best way to measure the strength of the deck concrete that's in place, which has a larger mass and more restraints? Does the deck have more strength or less compared to the cylinders? And we use these to open the deck. Are we doing it too soon sometimes? Also, when you think of construction inspection during the deck pour, if metal pans are used for the decking, do we know if that concrete is consolidated properly throughout the bridge? And then looking after construction, if we're doing those routine inspections of the deck, how confident are we in the rating that inspectors, if they can't see the underside of the deck because of a stay-in-place form, it's really difficult to assess that condition. So we're going to talk about the I-469 project that incorporated three technologies into a single bridge to help the Indiana DOT address some of these problems I just mentioned. So transparent stay-in-place forms, E5 internal cure plus liquid fly ash, and then GITEC and WaveLogic sensors for measuring maturity and strength. So while Indiana DOT had used transparent stay-in-place forms on an ITD project previously, and they had also used E5 internal cure previously, they had not had the combination of E5 with the liquid fly ash, and then they had never used WaveLogic sensors to measure the in-place strength of the deck concrete. So I'll be discussing the transparent stay-in-place forms, then I'll bring Robert up to talk about the other two. So this project was a bridge replacement along a major highway in Fort Wayne, Indiana. It was a 3-span bridge composed of bulb T beams. It was built in 2 stages. The eastbound was in the spring of 2021, the westbound in October of 2021. So TrueTech Bridge, we designed and supplied the transparent stay-in-place deck forms for the project. These forms allow for inspection of concrete during the deck pour such that any honeycombing or pore consolidation is avoided. They eliminate the need to strip forms from below, which reduces any risk to the contractors over traffic, railroads, high heights, and they also allow the owners to see the underside of the deck during those routine inspections to accurately determine the condition state. So here's a short video of the 2 stages being constructed. So we supply the shop drawings and we prefabricate all the forms custom to each project. We deliver those forms on pallets to the contractor when they're needed. This project was 6,300 square feet of panels. Each panel was 6 foot by 4 foot and weighed approximately 75 pounds each. So easy for 2 people to pick up and put in place on the bridge. It took a crew of 3 about 2.5 days to install each stage. We supplied skewed forms at all the abutments and diaphragms to help keep all the construction forming top down. Rebar installation's exactly the same as any other forming system, except we do kind of tighten up the rebar chairs to keep some of the high stresses off the top of the plastic sheet. But the deck pour went really well for both the eastbound and the westbound, being the first time with this contractor, and also using the mix design that Robert's going to talk about here soon. So this project did attract a lot of attention from personnel within construction, preservation, inspection from Indiana, not only the district but central office as well. So being below the bridge deck, seeing the placement, it's a very unique view. So if you ever get a chance to visit a bridge, I suggest you do so. But Keith Lighton, NDOT's asset management and bridge preservation engineer, shared this quote regarding the ability to inspect during the deck pour. Keith also gave me an update on the status of the most recent inspections, which he said both decks, the underside of the deck and the forms are in great condition after 2 years, and they're both still rated as 9s. So transparent forms helped Keith address his concerns of deck quality during casting. He likes knowing he can see the underside of the deck in the future for inspections because he is concerned that some of his 30 or 40-year-old decks with corrugated metal, he doesn't know the condition. So this is a solution he would like to continue to see in his district. In terms of what's next with Indiana DOT and transparent forms, last fall they did a large bridge replacement along I-69 over a river crossing, and they gave the contractors an option to use either form and strip it with lumber or use transparent stay-in-place forms because NDOT wanted to see the bottom of the deck on this bridge. And so when it went out to bid, the low bid contractor actually chose to use transparent stay-in-place forms, and this job's under construction, stage 2 of 4 currently, and is going really well. So with that, I'll transition to Robert to share more about internal cure and the sensors technologies that were used on this project.
Thanks, Dave. Good morning, everyone. My name is Robert Cavaliero. I'm responsible for business development for Specification products. Today we're talking about this I-469 twin bridge replacement project for Indiana DOT, and it's awesome to be here at this conference because Indiana is where our company is, and we've gotten a huge amount of the initial traction. And Indiana has been very aggressive with their bridge preservation techniques. And to Dave's point, both from the initial design, underlying structure, formwork, to the concrete mix design, as well as some things to help to accelerate the schedule down the line. So Dave talked about his TrueTech clearcast decking, which I could watch videos of all day. It's like being trapped under the concrete coming into, I don't know, it's incredible. I love those videos of your product. We'll discuss the E5 nano silica-based products, the internal cure and the liquid fly ash. And then the non-destructive testing was not something that we were immediately involved with, but it was a collaborative effort between Indiana DOT and Purdue with Dr. Luna Liu in their ongoing effort to further develop better bridge preservation techniques. So prior to the I-469 job, Indiana DOT had quite a bit of experience with these E5 products. The E5 internal cure specifically They started using and did their first bridge trial, I think, in 2016. Quickly recognized the benefits and the potential of it, and by way of memo, not specification, and after seeing about 80 bridges in place with 30 to 60% reduced cracking, they wrote a memo that allows contractors an alternative to 7-day wet cure. So you use the E5 internal cure, it consumes the water of convenience, so there is no bleed water, and ultimately you can remove the 7-day wet cure process. The materials, the cost, the carbon footprint, all of that. With the I-469 twin bridge replacement, this was going to be the first project where they actually used both the liquid fly ash and the internal cure product together. And they both have individual benefits, both to fresh and hardened properties. So the internal cure, what's it do? It controls the water, right? It cures the concrete from the inside out, right? These are Dr. Jason Weiss and Dr. Luna Liu's words. They've done years of research on these products and they firmly stand behind them. The liquid fly ash, it actually consumes the calcium hydroxide to form new calcium silicate hydrate in existing concrete. Individually, fresh properties, the internal cure, because that water of convenience is not evaporating, it's being contained within the concrete, slump retention is not an issue. Folks don't have to add water when the truck arrives halfway through the discharge. They don't have to add it to the surface. These products were created by a third-generation finisher for finishers. They're meant to make placement and finishing easier and make concrete more durable so the finishers don't get callbacks later because the concrete is not performed well. So it eases placement and finishing, right? When you put these chemicals into concrete, the hydraulic pump pressure will drop. Traditionally, it might be running at 4,000 PSI. You put these products in, it'll drop to 2,800 or 3,000 PSI. You can pump these products because they become creamier. They're easier to move and finish. That translates into the hose, right? They can be pumped further horizontal distances, higher vertical distances. Because that pump pressure comes down, that's better emissions, that's less fuel per a given yard of concrete to be pumped, and ultimately that equipment can maintain service for a longer number of service hours. We've seen folks who have taken pumps out of service after a certain number of service hours. Once they adopted the E5 products, they brought those pumps back into service because they can pump those mixes more efficiently. So it helps that contractor again. Hardened concrete, reduced shrinkage, improves the surface durability. The E5 liquid fly ash. Dr. Jason Weiss says it's a direct replacement. It is a liquid supplementary cementitious material, right? It can be used to replace SCMs. It can be used to reduce cement. It's consistent and readily available. One tank of this can replace 28 tanker loads of fly ash from being delivered to a concrete plant. It has no influence on air content. Imagine using an SCM that's always available. You don't have to chase air. You don't have to lose loads. That's what our producers are experiencing. Lost loads are no longer an issue. In the hardened concrete, it reduces the permeability, as you would see with traditional fly ash and supplementary. So to go out onto this job, we did quite a bit of lab testing, right? In those 80 bridges, we had just used the Indiana bridge deck mix that you see there in that column that is essentially with a type 1 boozy cement. Now these numbers change with a 1L, this was done a few years ago. It was a 658 type 1 with 20 pounds per cubic yard of microsilica with a 0.42. In the memo that Indiana DOT wrote, allowing contractors to use these products, what they have allowed is that you can now use a water to cement ratio up to a 0.49, because over the course of 300 decks now, they've observed that that higher water to cement ratio, the water is consumed, does not create a problem with durability or degradation down the line. So you can see here that we optimized the mix. We didn't just add these chemicals in there to try to increase strength. We dropped 78 pounds per cubic yard of cement, and we removed the microsilica 20 pounds per cubic yard. So we've taken about 15% of the cementitious content out, and we increased the water to cement by 12%. So we've done some good on the materials. You look at the destructive testing, you see that line of compressive strength results. 6,200, we dropped 15% of the cementitious content and increased the strength by 6%. Qualifies for a 5,000 through ACI 318. I think you need 6,400. So we had a little bit of buffer there. The anomaly lies in the flexural strength, right? This is a 600 PSI at 28-day design. Their mix got 720. That's pretty expected, right? Pretty reasonable. Our mix got 1140. It's great to increase flexural strength like that. Great to improve the cement efficiency 20%. But is that a problem, right? You don't see this regularly. So we were a bit concerned. We ran the calculations to determine conservative versus a little higher flexural strength based on compressive, and our numbers still far exceeded what we were measuring and what the third-party lab measured. So what do? You pull cores. You send them to Dr. Luna Liu. You say, Luna, what are we doing here? Are we in trouble? And Luna says, no, there's no issue. You guys are in good shape. There's 3 phases of concrete. You may have only learned about 2 in school, the mortar fraction and the aggregate. But there's the interfacial transition zone, this ITZ, which is the immediate area around the aggregate where the cement paste bonds to that aggregate. And in this area is a significantly higher water to cement ratio and abundance of calcium hydroxide. She refers to the ITZ as the weakest link in concrete, the failure mode in concrete. Well, if you look at this diagram, what happens is that the bulk cement particles are kind of on the outside. They're the runt trying to get in, and they're too big to fit in the 40 micron space that's up close in the ITZ, where that excess water and calcium hydroxide is. Nanosilica particles are doubly negative charged, and they're anionic, and they're attracted to water, and they're much, much smaller than cement. So they weave their way into that area, and where that water and calcium hydroxide is becomes ideal locations for heterogeneous nucleation sites. Essentially, the nanosilica consumes the calcium hydroxide to form new calcium silicate hydrate. When you improve the ITZ, you experience an enhanced aggregate bond. You reduce microcracking, you improve the resistance to abrasion, and you improve the concrete ductility. This concrete was able to bend more, and the aggregate didn't pull out before it failed. Forgot to say, that's a 1-day break with the E5. Look at all that aggregate fracture in there. Usually you see a lot of pull out at that break. So if you look at the interfacial transition zone, you can see that here on the right-hand side that the E5 mix has a much more cohesive, uniform bond to the aggregate, and around the NDOT bridge mix, you can see almost a gap, right? A space there, which is where that failure typically occurs. So here's just some pictures from the project. I had a picture in here of sensors, but Dave stole my thunder, so I removed that one. I have a blank space here. This is what you see on E5 projects. Folks are comfortable. They're not running. They're not freaking out. They're not throwing water. Oh yeah, the memo with Indiana DOT, no water is allowed to be added to the surface on the job, and a water reducer is allowed, no water reducer is required because the E5 brings that in. It brings that property in. So what did we save? When you wet cure, our contractor uses about 5 pounds of water or 0.6 gallons per square foot. Across 14,000 square feet, we saved 8,300 gallons of water. I live in Colorado. Water's a big thing. It's been a big thing for a long while. Cement, aggregate, those are all the topics of today. Water will be a problem. We will be talking about water in the years to come. Keep in mind, if you can save water, you will be in a much better position down the road. Cost savings, the mix was $35 cheaper per cubic yard. We saved over $16,000. Am I okay on time? Okay. Time savings, right? These products are for the finisher, for the installer, so they can do it easier and faster. They can place and finish more in a given day. They are able to cut 7 days off the cure time. They cut more than a week off of the construction schedule. When you talk about carbon footprint, sustainability, we're able to accomplish this from a couple different ways. When we talk about materials, right, cement's the hot button, concrete, right, 1 to 0.92, whatever, 1-to-1 ratio of CO2 to pound of cement. We saved about 90 pounds of CO2 per cubic yard, or about 43,000 pounds of CO2 from going into the atmosphere for this project. We saved over 37,000 pounds of cement and 9,000 pounds of microsilica. That's a lot of material still sitting in the silo at that producer to use for your next job, right? No worry about running out of materials. Allocation's not an issue. Transportation, those materials have to get to site. The cement, the microsilica, it's got to get to the concrete plant. That water, that 9,000 or 8,300 gallons has to get to the site. That's trucked in. It's used for wet cure. It's got to be reclaimed. It's got to be trucked off the site to be treated and recycled. And you're probably not getting the wet cure that you actually paid for. So when we talk about the sensors, a third innovation or fourth innovation almost that NDOT was looking at, they're working a collaborative effort with Dr. Luna Liu and Indiana DOT for the last several years. This was one of the earlier projects on there where we had done the destructive testing, the compressive strength, and the flexural. Luna was developing these Rebel concrete sensors made by a company that's now named WaveLogix. And she wanted to do some development work on this project. And Dave showed a picture of these sensors attached to the steel, the Geotech Smart Rock with the Rebel. And you know, the Geotech, you basically do a bunch of testing, establish a time temperature curve, embed these in situ sensors, monitor the time temp, and you can spot when you hit the compressive strength of the design and open to service. It should accelerate your construction schedule, save on resources having to break. Luna's attempt is to use this piezoelectric sensor. It measures direct in situ stiffness and correlates it to compressive strength. The beauty of these sensors is there's no preliminary testing and batching required. You don't have to develop that curve beforehand. So while it's not exactly the same measurement, it should remove a lot of the initial work that's necessary to get good results with the maturity sensors. Dave?
Probably running out of time, but I just want to thank the partnership very much for allowing us to present, and feel free to contact us at the exhibit hall if you have any questions. Thank you.